Hi everyone. Today we are lucky to have Ramon, and he'll talk about the Minkowski monotonicity problem. Thank you very much.
Thank you. So, yeah, thanks for inviting me. Yet another seminar at IAS. A couple of weeks ago, I gave a member colloquium about an old question of Minkowski on convex geometry, and this dates back to a paper, a 1903 paper of Minkowski. And today I want to talk about the different open problem that comes from the same paper of Minkowski that also remains open. And so this is a question in convex geometry, and it's really a question in geometric analysis. And in a sense, it's much closer to analysis and to PDEs, and I'm going to try to present it from this perspective. But we have to start from the beginning and write down the basic questions. So bear with me as I remind you of some of the basic notions that arise here, and we'll work our way towards the more analytic question. So we're talking about convex bodies. So let's K1 to Km be convex bodies. And right, so convex bodies are just convex compact sets. And the basic starting point here is the observation of Minkowski that if I take the volume of convex bodies, it's actually a polynomial. So if I take the volume, let me write it here. If I take the volume of a linear combination of convex bodies, so it just means I take one point from each of the bodies and I take their linear combination of the fixed coefficients lambda 1 through lambda m. These are non-negative coefficients. I take the set of all of those. It actually is a polynomial of degree n. N is the dimension. It's a homogeneous polynomial of degree n. So it's a sum of I1 to In from 1 to m, lambda I1 times lambda I2 to 1 lambda In. These are the monomials. And then there are these coefficients which depend on the bodies. These coefficients, they're called mixed volume. And they are basic geometric functionals associated to convex. Okay, and many of the geometric functionals that we know and love are actually special cases of these coefficients of the volume polynomial. So these coefficients are the things that we're trying to understand. And so Minkowski realized that there's a lot of geometry encoded in these coefficients. These coefficients, they have some trivial properties. For example, they're linear in each of their arguments, so they're multilinear. It just follows from the definition. They're symmetric in their arguments. It also follows from the definition. They're non-negative. That's not so obvious, but it's true. But they have some non-trivial properties. So let me write them down here. So being non-negative is actually a non-trivial property of these things. I'm going to write them more generally, yes?
Is there any way to make sense of this when some of the lambda i's are negative?
So it's not true. I mean, if one of the lambdas is negative, you can just view this as multiplying the points by minus. But it's not true that this is a polynomial on all of Rn. It's only a polynomial in the positive cone. Because, for example, if this is a symmetric convex body, right? If I replace lambda by minus lambda, nothing changes, right? So you can see that it doesn't behave like a polynomial.
Yeah.
Does that make sense? So if you want to think of it as a polynomial, you have to think of it as a polynomial in the positive cone. That's how we do it. Of course, you can make the lambdas negative. It just won't be a polynomial as you pass through. So I'm going to give an example in a moment, but what are non-trivial properties? The most non-trivial property of these coefficients is that they're law concave in the following sense. The mixed volume of KL C1 to Cn minus 2. So a mixed volume in dimension n is a functional of n convex bodies in Rn. And they satisfy this law concavity property. And this is called the Alexandrov-Fenchel inequality. This is a very deep inequality that has many connections with other areas of mathematics. So, and I talked about that a few weeks ago. But there is another non-trivial property that's actually much easier than this inequality. And And it's the following. If K is a subset of L, then the mixed volume of K, n minus 1 other bodies, is upper bounded by the volume of L, n minus 1 other bodies, and this is just monotonicity. Mixed volume is monotone in each of its arguments. If I make a body larger, if I make K larger, I also increase the mixed volume. So this is much, much easier to prove. We just need a formula for the mixed volumes to see this. It's much easier to prove, but it's a non-trivial property of mixed volumes. It's not something that would be obvious just from the fact that we have polarized here. And the special case of this second property is, in fact, that the mixed volumes are non-negative. Because, for example, I could just take K to be just a single point inside the set L, then this mixed volume is always 0. And then I see that the mixed volumes are non-negative. Okay? Now, the very fundamental question that dates back to Minkowski.
Sorry, maybe it's stupid. Like for a point is 0 again.
Because you see, if one of these guys is a point, then this is just translation, and the volume is invariant under translation. So the coefficient, any coefficient, this coefficient lambda, if I have this, the mixed volume of K1 to Kn is just the derivative, the nth derivative of the volume with respect to lambda 1, lambda 2 until lambda n. So if one of them is a point, then by translation invariance of the volume, it's a good question, right? The mixed volume is always okay. However, what's not true, just to be clear from the very beginning, is that you see the volume of a convex body in Rn is always 0 if the body is less than n dimension, right? If I have an n minus 1 dimensional body in Rn, the volume is 0. That's not true for mixed volumes. So it could be that all of the bodies here are all lower than n dimensional, and the mixed volume is still non-zero. Because you see, I can take 2 lower dimensional bodies, let's say in R2, I could take 2 one-dimensional bodies in R2. If I add them up, I get something with non-zero thing. Does that make sense? So it's not true in general, right? Unlike for the volume, right? All of these bodies could be, let's say, of codimension at least 1, and it is still the mixed volume is not true. Good. So there's a basic question of Minkowski is, when do these inequalities achieve equality? It dates back to Minkowski's original paper. And for the Alexandrov-Fenchel inequality, I discussed this at some length a few weeks ago. And there, even for the very simplest kind of bodies like polytopes, this was completely unclear. And we made a lot of progress on that with Yair Shenfeld. So that's a kind of this Alexandrov-Fenchel inequality. You can think of this as a kind of generalization of the isoperimetric inequality, and the equality cases are really like the solutions of the isoperimetric, strange isoperimetric. On the other hand, the second inequality, this much simpler inequality, even for that inequality, the equality cases have not been characterized. And this is a much easier inequality than the first inequality. Now, the problems are a little bit different, right? So for this inequality, we did not even understand until recently the combinatorial aspect of the problem. Okay? So for example, if all of the bodies are polytopes, this is really a combinatorial problem, and that was not understood. In the case of polytopes, it turns out that this problem is very easy. So here, it's really a different question. It's really a question of analysis. If you have very strange convex bodies, right, which are not polytopes, right, but which are kind of very non-smooth, let's say, convex bodies, and you'll see that later on, that's really the situation where we do not understand this. So it really lies in the analytic side of the theory that we have a lack of understanding of convex bodies. But this will become much more clear by the end.
So here, you're implicitly saying that we understand that both for polytopes and for smooth objects.
Yes. Okay. Even for smooth, depends on what you mean by smooth. You will see later. We do not entirely understand. Depends on how smooth. If they're really smooth, yes, we understand. If we're really smooth, we understand completely. If they're polytopes, we understand completely. You will see later on.
Yeah. So you need some strict convexity or so.
Smoothness, it's a definition. A convex body is called smooth if it has only one-dimensional normal cones. So that's a form of strict convexity. That's in convex geometry, that's the definition of the words. let me give an example. I like this example very much. It was cooked up by Shouda. So let's do it in R3. So this is actually the setting that Minkowski was originally working in. So let me give you an interpretation of two of these mixed volumes. So if I take the mixed volume of a convex body K and B. So whenever I write B, it's always going to be a Euclidean unit ball. Okay, in R3. K is an arbitrary convex ball. So this turns out to always be 1/3 in the case of R3 times the surface area of the convex body K. So we can interpret the surface area of a convex body as a special case of one of these mixed balls. Now, what we could do instead is we can take this mixed volume. Okay, so now I took the convex body K and I took two balls rather than one ball. And there's some other constant. These constants don't matter. This turns out to be the mean width of the convex body. Right? So again, what is the mean width? I take a body, pick any direction, just look at the width of the body in that direction. Just take two planes and look how far apart they are. You can still fit the body, and then average them over all direction. It's called the mean width. So what is the second inequality saying? So even this kind of trivial monotonicity, it looks kind of trivial, right? Because we know that volumes are monotone, so it looks kind of, maybe expected that mixed volumes will be monotone. But it's giving us non-trivial geometric inequalities for these kind of, right? So what do we know? For example, suppose that I know that the convex body K is contained in the Euclidean unit ball. That just means that the out radius of this body is 1, right? So if the out radius of the body is 1, then what do we know? Well, then you see K is contained in B, right? So it means that S of K is less or equal than 2 pi of W of K. So it means that the surface area, if I have a body with out radius 1, then the surface area of that body is bounded by 2 pi times the mean width of that body. And it's an immediate consequence of monotonicity, right? Because you see these two guys are the same, these guys are the same, and this one is smaller than that. And of course, I could make this inequality homogeneous if I wanted, right? Rather than assuming this, I could just write basically that the surface area of K is bounded by 2 pi times the out radius of K times the mean width of K, right? So it's, yes.
And this same inequality, I guess that one could obtain something along the similar lines by radial integration.
Yes, because essentially it turns out when we write down what these mixed volumes are, they will turn in this special case into these kind of integrals. Okay, but indeed, yeah, it's not a especially deep inequality, but we get it immediately as a special case. Now, on the other hand, if K contains the unit ball, that means that the in radius of K is 1. Right? So here we're talking about out radius being 1, here we're talking about the in radius being 1. Right? Then the inequality goes the other way. And again, it's an immediate consequence of monotonicity, just go the other. So these are two very similar looking inequalities, but depending on whether we bound by the out radius or the in radius, we get an inequality in the different direction between surface area and mean width. And now you can ask, when do you get equality? Now, these inequalities look very much the same, right? These inequalities are the same inequality, really, in some sense, right? They look very much the same inequality. But they behave completely differently from the point of view of the equality case. Right, so the equality cases here say that if I take all bodies without radius 1, let's say, and I fix the mean width, which one maximizes the surface area? That's how you could think about these kind of questions. And here you can think about which one minimizes the surface area, right? If I fix the in radius. So it turns out that the answers are completely different. Okay, so in one, we have equality if and only if the body itself is a Euclidean ball, up to a constant. up to scaling and translation, because these things are, yeah.
It's already contained in the ball.
Oh, it's already contained in the ball, so we're very good. Okay, so it's even if K and B, very good, because we already fixed this. Good. So the equality only happens when the K is a Euclidean ball. That's something that you might expect It's kind of from isoperimetric typing. However, in the second case, the equality, there are many more equality cases. And in fact, these equality cases are the same equality cases that one gets for the Alexandrov-Fenchel inequality. So I drew them in some previous talk. They look like these objects with these party hats on, right? You take a ball and put a bunch of party hats on it, and you will always get equality in the second inequality. So you see, you get very strange equality cases for the second inequality. You get only trivial equality cases for the first inequality. And these inequalities look exactly the same. So something already strange is going on. These are very basic questions. You know, these are the first, when you have kind of sharp inequalities like this is kind of the first question that you ask is, you know, what are the extreme cases of these inequalities? And already you see a kind of a strange picture showing. So in this case, this is a theorem. It follows from known results. But in general, like the problem here is open. And one would like to have a geometric characterization of when you have equality for the monotonicity of mixed volume. This is Minkowski's monotonicity. Are there any questions? So let me try to move towards a more analytic understanding of this point. So let's try to reformulate this problem. So,
is it obvious to see that this would be equality case in hat, or it's a calculation?
neither. It requires some understanding of what's going on. So I you know, it was known to Minkowski, but it shouldn't be obvious to you. It's certainly not obvious. So maybe by the end of the talk, you can ask me again, and we can go back to this example, which would be a good exercise for understanding whatever. So let me remind you, first of all, of a property that's very basic by definition of mixed volumes. Right? So if I take the mixed volume of K plus L, this is the mixed volume of K plus the mixed volume of L, right? So mixed volumes are added. And this is an immediate consequence here of the definition. This is nothing else than this. And this is the polarization of the volume. It's always going to be. So whenever you have something additive, we want to reformulate this as an analytic problem. So we want to represent our convex bodies in a useful way. And now we do a standard thing. It's standard nowadays, but in fact, it appears in Minkowski's. In 1903, this was not so standard. We introduced the following object called the support function of a convex body. So the support function of a convex body, so for any convex body K, we define the support function, which is a function from the unit sphere. And it's defined as follows. Xk of x is just the soup over all points in the convex body of the inner product of y. So we think of this as being a function on the unit sphere. And just so we are on the same page, should be convex. Here's a convex body K. And let's pick a direction x. Direction x, so this is supposed to be a direction in the unit sphere, right? So it's a direction. And suppose that the origin, let's say, is over here. Here's the origin. So what is this hk of x? Well, let's look at the supporting hyperplane of this body with this normal direction. So which way does it go? So it's this one. So you see this. This is the hyperplane with normal direction x that touches the body. It's called the supporting hyperplane of the body. And we can take the distance of this hyperplane to the origin. Let me draw another one of these planes for the origin with the same normal, right? So this distance over here is hk of x. So hk of x, what does it tell us? It tells us in every direction how far is the supporting hyperplane of the body of the convex body from the origin. And that means that this function contains all the information about the convex body. Because by convexity, a convex body is just the intersection of all of its supporting half spaces. So if you know where each of the halves of the supporting hyperplanes are, you can reconstruct the convex. It's the signed distance, technically. But if the origin is inside the body, this distance is always positive. Very good. Now, why do we need this object? So this support function contains all of the information about the body. Moreover, it has the property that if I take the sum of two convex bodies, then the support function of the sum is just the sum of the support functions. This is obvious from the definition. You just look at the definition over here. So this is a representation of convex bodies that's itself additive, which means that if I view the mixed volume, so if I fix n minus 1 bodies and I view the mixed volume just as a function of k, is that this mixed volume can be viewed as a linear functional on the support. That's just just an immediate consequence of the definition. And once we have that, we have the basic fact, Reeves representation theorem. I mean, of course, I'm skipping some technicalities here because one has to, check that this is a continuous linear function. Well, it turns out to be easy, okay?
And also defined only on some set of
It's defined, okay. What I should tell you, which is maybe not obvious at this level, is that indeed these functions form a cone, okay? But I can extend this by linearity to the linear space spanned by this cone. And that linear space is dense, let's say, in the space of continuous. So in fact, we are not missing anything substantial.
A cone again?
Well, I mean, it's in order for a function to be a support function, basically it has to be convex and non-homogeneous. So that gives that's a cone, right? If I take minus a support function, it's not a support function. However, every C2 function on the sphere can be written as the difference of two support functions. This is very easy because I take a C2 function, its Hessian is just bounded uniformly in the sphere by compactness. So I can just add and subtract a large multiple of the identity, right? And then I've written it, right? If I add a large multiple of the identity, it becomes convex, so it becomes a support function. And the identity itself is also, this is the support function of this is the Hessian of the support function of the Euclidean pole, right? So the upshot of this story is that we have a representation of mixed volumes. That the mixed, for every choice of convex bodies C1 to Cn minus 1, there exists a measure that I can represent the mixed volume. Okay, it is customary to write here 1 over n, but that just doesn't help. N is the dimension. That's just a customary normalization. It's the integral of the support function k with respect to some measure which depends only on these other bodies. And this integral is over the sphere. So you should think of this as a measure. This is a measure on the unit sphere.
positive.
And the fact that this measure is positive, which is not obvious, it has to be checked. But the fact that this measure is positive is exactly equivalent to the statement that the mixed volumes are monotone. Because if I increasing a convex body is the same as increasing its support function, right? Because the support function is a soup. Right? And therefore saying that this is monotone is exactly equivalent to saying that this is a positive. This measure is called the mixed area rule. And in general, this is a nasty measure. Okay? So, I mean, nasty. What is nasty? It's a Borel measure. But it doesn't have any other nice properties. In fact, one of the classic questions in convex geometry is Minkowski existence the Minkowski existence theorem says that any Borel measure on the sphere that has barycenter at the origin can be represented as such a measure. In fact, even with the same body. Right? So these measures can be as nasty as any Borel measure on the sphere. They're just required to have their barycenter.
Let me just repeat the last statement. So any Borel measure with barycenter that is correct and non-negative can be represented like that for a given convex body C repeated n-1 times.
We do not need to write it. We do not need it in this talk, but let me just write it because it's good to know. It's called I'll put it between brackets. For all measure on the sphere, such that the integral of any linear function there, right? It just means the barycenter is at the origin. There exists a convex body C such that mu is S C repeated n-1. It's called the Minkowski existence problem. It's one of the classical theorems of convexity. And the regularity of this measure has been a major subject in the theory of nonlinear PDEs studied by Nirenberg and various other people. And so if, for example, what you could ask is if you start with a measure that has a smooth density, right? How smooth is that convex body? And that's one of the kind of classical problems that's in a lot of theory of nonlinear PDEs in the 20th century. So the point is now that we can equivalently reformulate the equation.
Just one more check to understand. There are n is appearing twice, but that's just a type. It's not important, right? There is n is the number of bodies and the dimension, but it's not important or it's crucial.
A mixed volume.
Oh, sorry, yes.
Where in dimension n? It's n because it's a polynomial degree n. Yes. So in dimension n, there are always n bodies. So yes. Yes.
I had the same question, but I didn't understand the answer. Further, why are we taking n bodies in Rn? Is it trivial if we take less? Is it obvious? It's impossible to take more?
The mixed volumes, by definition, in Rn, by definition, they have n slots. You put a convex body each. The reason is that the volume of a sum, when I took the volume of a sum of convex bodies, I didn't take n, I took an arbitrary number.
Yeah, okay.
But it's a homogeneous polynomial of degree n. So these are the coefficients of the monomials, and the monomials are exactly a product of n of the lambdas. So they have to have n bodies. Does that make sense? Okay, good. So for example, if you took the volume of a linear combination of more than n bodies in Rn, right? Then you would get mixed volumes of subsets of those bodies, which would then be the coefficient. But if you took less, then you would get multiple bodies repeated, right? Does it make sense?
Yeah.
Okay, so here's a reformulation of the problem. We haven't gained anything, okay? So what does it mean? So suppose that K is a subset of L. This is exactly the same as saying that HK is less or equal HL pointwise. This is exactly the same statement. So saying that the mixed volume of K C1 to Cn minus 1 is less or equal mixed volume of K of L C1 to Cn minus 1 is equivalent to saying that the integral of HL minus HK ds C1 Cn minus 1 greater or equal to 0, right? For all K and L. Right? But because we can write any C2 function, let's say in this form, right? That's just equivalent to saying that this is a positive measure. Now the question is, what happens when you have equality? Right? So that's equivalent to having equality here. But L is greater than K. So this is a non-negative function. This is the same as if I have the integral of a non-negative function equals 0, which means that the integrand must be 0, but only on the support of this measure. So the point is, we have equality of monotonicity if and only if HK of x equal HL of x for all x in the support of this measure. And the question is, what is that? These are measures, they don't have to be supported everywhere in the unit sphere. They can be supported in a very small subset of the unit sphere. For example, when these C1 to Cn minus 1 are all polytopes, this is actually a finite measure. It's only supported on a finite number of points. So the real question here, which is equivalent to the question of equality, is to characterize the support. The support of this one.
I'm still worried about the fact that we are living in a cone. So when is HK at the boundary of this cone?
But we are interested in the space of differences of support functions. Of
Yes,
functions.
but
they don't live in a cone. They live in
is
unit.
HK being in HK is on the boundary of this cone,
Mhm.
you might not remain into this cone, or
Right.
do you?
So are you saying that HL minus HK is not a support function?
No, I'm
That's
telling
fine.
that if I add to HK something positive, I
Yeah.
might no more have a support function.
That's true.
Yes, but then
Let me just write, I said it in words right here. It's not 100% obvious, but it's an easy fact. For all f C2, that's very important, function of the sphere, there exists convex bodies K and L, such that F is HK minus HL. Now, of course, the opposite is not true, right? So if you take support functions that are not C2, of which there are many, right, you do not necessarily have an analogous statement. But in order to, it's not a problem for us, right? I mean, for example, if you wanted to show that the inequality here, that this is greater or equal than 0, implies that this is a positive measure, it's enough to test that on non-negative C2 functions. Right? And therefore, you reduce back to the statement about convex. So that's usually how we do the translation. But for the statement I wrote here, you don't need anything because, right, I mean, we already know it's a non-negative measure. Right? And we just want to show that we have this minus that equals 0, right? So it's already a non-negative function. It doesn't matter which non-negative function. I gave you two convex bodies, so you get a non-negative function. And therefore, this is true if and only if the functions agree on the support. Does it make sense? Yeah. So the real question here is to characterize the support. Because you see, once you characterize, if I can characterize the support geometrically, there's some subset of the unit sphere, then this gives us a complete geometric characterization. Because it says that those two bodies must have the same supporting hyperplanes in those directions which are in the support of that measure. So the only question here is to characterize the support of that measure. Right? That's the question that we have to answer. And I now want to try to explain to you what the nature is of this problem and what its connection is to classical geometry. So one of the big issues that we have is that we have in general, if I give you general convex bodies C1 to Cn minus 1, we don't have any useful formulas for these mixed area measures. They exist, they're measures, but we don't have any explicit description. We only have an explicit description of these measures for certain nice situations. So one of the nice situations where we have an explicit description of this measure is when all of these bodies are polytopes. And for that reason, when all of these bodies are polytopes, we can very easily solve that problem. That's not a problem. That was a big problem for the Alexandrov-Fenchel inequality. That's not a problem here because we have explicit formulas. And whatever conjectures I'm going to write down later are consistent with those explicit descriptions. Okay? But already when we have smooth bodies, we get in trouble. Okay? So not smooth, but when we have smooth support functions. So let's first talk about the simplest and most classical case that we could think. Suppose that I take a convex body, let's say C, such that HC is C2. Suppose I take a convex body so that the support function is twice continuous once. Now, anytime, in fact, you will see later that we have a formula for this. When all of these bodies have C2 support functions, we have a formula. But let's just think about this case that I wrote up there, where all of the bodies are the same. That's the simplest case. Let's study that one. Then we have an explicit formula. So now I took all the bodies, I took n minus 1 copies of C. In this case, this measure has a density with respect to the uniform measure on the sphere. And the density is nothing else than the determinant of the Hessian of HC. So when I write d omega like this, I just mean the uniform measure on the sphere. So this is an absolutely continuous measure, and its density is the determinant of the Hessian. Now, we have to worry a little bit about what I mean by Hessian. I don't mean here the covariant Hessian on the sphere. You can express this in terms of the covariant Hessian on the sphere. HC plus HC like this times the identity. So you need some correction for the curve. You can think of this as the Hessian in Rn. If I view the support function as a function in Rn, you can take the Hessian in Rn and restrict it to the tangent space of the sphere. Okay? So what?
One homogeneous.
The one homogeneous extension, right? Take the Hessian in Rn, take the restriction to the tangent space of the sphere, you get. I'm just going to call it Hessian just for it. But it's a standard object that shows up in geometry. Now, what does this mean? So let's think about this example. Just this very special case, we have this very special case where all of the bodies are the same. We have a support function that's C2, and now we want to understand the support. So what does it mean? Okay, so what does it mean for X not to be in the support of this measure? So what it means not to be the support of this measure, that means that there's some neighborhood of X for which the measure is 0. That's the definition of support, right? There exists some neighborhood, some open neighborhood of X, such that but X has this density, right? So what does it mean? It means that the density vanishes on that neighborhood. Determinant of the Hessian vanishes on some open set. This is nothing else than the homogeneous Monge-Ampere equation. Where's it good?
What's C again?
C is the convex body that we're interested in. So in this case, I'm thinking about the monotonicity of mixed volumes where I took all of these C1 to Cn minus 1 to be equal to one convex body C. Okay, so it's just a special case. This case we understand very well, but it's just a special case to understand the nature of it. So we want to understand what it means, right? What it means for a point not to be in the support. Well, that's the same as saying that the Hessian of the determinant of the Hessian vanishes in the neighborhood. Now, this is a very classical problem. And in fact, at least in 3 dimensions.
When you take the determinant, you first restrict to the sphere.
When I take what?
When you take this determinant, you restrict to the sphere.
Yes, this Hessian lives in the tangent space of the sphere at the point X. Yes, exactly. So it's an n minus 1 dimensional. So this problem over here, at least in 3 dimensions, is equivalent to a very old question from the 1700s, which is that to characterize surfaces that have vanishing Gauss curvature, because the Gaussian curvature of a surface can be expressed in terms of this. This was a problem that was studied by Euler. And Monge, the Monge-Ampere equation of Monge was developed for these kind of questions. And so this is work from the 1700s. And another reference that I think is very useful on the less regularity is of Hartmann and Nirenberg. Studied by many people, basically says, so I'm going to write it in a kind of geometric form. It says that the surface with vanishing Gauss curvature is a ruled surface. Well, basically what that means is that the surface is such that there's a bunch of it can be decomposed, it can be foliated into a bunch of lines where it behaves linearly. Okay? So it's like you take a piece of paper with all of its lines, and you can fold it up however you want. But you see, however you fold up this piece of paper, you're always going to have a bunch of straight lines, right? And that's called a ruled surface.
Which surface are you speaking of? Because there's a function.
So I'm just making an analogy. And in the case of surfaces, you would have to put here the curvature function of the, right? It's the same equation, just a different interpretation of what you plug into. So you can just translate what that means here, which is that so in our language, right, or in our context, it means that there exists a foliation of the, say the sphere, the straight line, such that HC is linear. So I can decompose, right? Basically, I can take the, how do I want to say it? I mean, it's easier to see when you fold a piece of paper, right? I mean, you fold a piece of paper, right? So you can take a bunch of straight lines. Sometimes you may have a flat part, right? Then you have a bunch of straight lines. So you can decompose it into linear parts. Maybe a better way to think about it is as follows, right? So let's think about it analytically. Let's think about it in Rn rather than the sphere. It's all kind of equivalent. I just think it's easier to think about. Suppose we had this in Rn. The determinant of the Hessian is 0 in Rn. What does it mean for the determinant of a matrix to be 0? It means it has a non-trivial kernel. Right? So there's one direction in which, at least one direction, in which the second derivative is 0. Now, functions whose second derivative is 0 everywhere are linear functions. Right? So this is a kind of local to global phenomenon. Here we're saying that kind of infinitesimally, there is a direction where infinitesimally, at every point, there is a direction in which infinitesimally this function behaves linearly. But what we're saying over there is that we can blow up this property to be global, right? Which is, in fact, we can foliate the domain into lines so that the function is actually linear on those lines, right? And that's the statement that is being made.
Why would it be a foliation into lines?
So not all of them are necessarily lines. Some of them could be two-dimensional, like I tried to draw over here. So they can't curve. They cannot curve. They have to be straight. And that's exactly this statement, this classical statement from geometric analysis. So there is a way of integrating this equation to take this local property, which is that at every point, the Hessian has a non-trivial kernel, which means that there is a direction where at every point there's a direction where the function is infinitesimally linear. There's a way of blowing it up so that you actually get a foliation by lines. And it's not, I mean, by modern standards, it's a relatively easy proof if you assume that the rank of this matrix valued function is constant, but that's not necessarily true in general. And that's what makes this problem.
From the sphere, what does it mean you are not curving? It that like some is a it's a
So you should think about this. You can either think about this support function as living on the sphere, but you can also think about it as a one homogeneous function on our end. And just think about it on our end. So let me write down geometrically what it means for the convex body.
Wait, but if I think about it in Rn, there is a trivial ruling. There is a trivial ruling. Just consider lines that go from the origin. But that is an empty statement, just because it's one homogeneous.
No, it has to be in the transverse direction. Right?
The determinant is taken, yes.
Yeah. Let me write out geometrically what it means for the convex body. Say we have a convex body like this. So remember, the origin is here. The convex body goes on. Right? So the origin is here. Let's fix the direction. So this is the normal direction of this plane. Now, remember that the distance to the origin, this is hk of x. So what's going to happen if we start moving x? You see, if we start moving x here, right, this plane is still going to touch this body at the same point because all of these vectors are in the normal cone of this body, right? So the normal cone of this body is this cone at that point. And as long as I move my vector inside the normal cone, it's always going to touch at the same point, and therefore the distance to the origin is going to behave linearly, right? So the support function, it's linear inside the normal cones of the body. As soon as I move from one normal cone to the other, that's no longer true. So saying that there exists a foliation, right, where I'm linear, means that the normal cones, right, so that means that all of the normal cones of the body must be at least two-dimensional. They cannot be one-dimensional normal cones. Because there must be at least one direction in which you can move. There must be at least one direction in which you can move at every point where the support function is linear, and therefore those must lie inside the normal cone. So
And like in that, at least in dimension 2, this immediately implies that you're a polygon, or I'm missing something.
Dimension doesn't imply no.
This falls in the
So dimension 2 doesn't imply you're a polygon. Dimension 2.
or maybe you put
No. We're talking here about just inside this neighborhood.
Yes.
So it means that every point in this neighborhood must lie in a normal cone. So it means that this neighborhood must be
Right.
covered by normal cones,
Right.
right, of dimension at least 2. And that covering is exactly the foliation that we're talking about. Makes sense? So basically, yeah, that's exactly what it said, right? So it's saying that the complement of the support, right? The point is non-insupportable. It means that in the neighborhood of that point, every point in the neighborhood of that point must lie in a normal cone of dimension at least 2. Now, this is in the case of smooth, right, C2 support functions. Of course, we don't care in general about C2 support functions. We want general support functions, right, which are not smooth. Nonetheless, in this specific case, the statement is true. So what we expect from this picture was proved by Schneider. It says that the support for any convex body, the support of the mixed area measure is the closure. The support by definition is closed, so we have to have the closure of all points x in the unit sphere, such that the dimension of the normal cone of that body with normal direction x is 1. So if you take the complement, what does it mean for a point not to be in the support? It needs to be in the interior of the set of all directions, such that the dimension of the normal cone is at least 2, right? And that's exactly the statement that we expect by looking at this classical picture. Now, the point is, this is true even when you take an arbitrary convex. Now, there's a big difference between the story over there of Euler and Monge, etc., and the story that we have, because they're not assuming that we have a convex surface. The statement there is for any surface with vanishing curvature. Here we have convexity, and convexity makes the story much easier. The solution of these kind of Monge pair equations for convex functions is very easy. But we are allowing ourselves to work with non-smooth bodies. And as you will see in a moment, the real question we care about is one that is much more difficult. Okay, so for solution, yes.
So you are having a foliation on the sphere,
Yes,
right? And they look like normal cones.
they are normal.
They are normal.
The foliation are it's foliated, so the sphere is foliated by the normal cones of the convex body.
So I'm trouble, so
So the normal cones live in Rn, but you can just, they're cones, so you can just take their intersection with the sphere.
Uh-huh,
And that gives you a foliation of the sphere, right? By the normal cones of the convex body.
okay,
Does that make sense?
yes,
And what this statement is saying is that the point is not in the support of this measure. If in the neighborhood of that point, you only see leaves of the foliation with dimension at least, well, if you think about the substance sphere, dimension at least one. You do not see singletons, right? You do not see rays of the normal thing. Does that make sense? Now let's get to the real problem, or part of the real problem.
Beforehand,
Yes.
can you tell what it means for polytope?
For a polytope, you don't need the closure because the support is just a finite set of points, right? And a polytope has a finite number of normal cones of dimension one. Those are the normal cones of the facets. And then this is saying that the support of this mixed area measure is exactly the set of normal directions of the facets of the polytope. And that's the state. And we're saying this is true for any convex body, no matter how non-smooth, as long as you take the closure. And of course, now you don't have facets, but you still have points, regular points of the body, which have the normal cones of dimension. Now, very good. So now let's try to get to a kind of conjecture. So now suppose that we have n-1 convex bodies. But let's still assume that their support functions are CQ. Now, if their support functions are C2, then we can get from this formula, we can get immediately a formula for the mixed area measure. Because you see, just by the polarization, just the fact that the volume is a polynomial means that these measures are also polynomials. So I can just replace this C by a linear combination of C1 to Cn-1, and then again expand this as a polynomial. So let's see what happens. So for this, I need the definition. If I take the determinant of a linear combination of a bunch of matrices, so these are n-1 by n-1 dimensional matrices. The determinant of an n-1 dimensional matrix is a homogeneous polynomial of degree n-1, right? So I can just polarize the determinant. I can write this as the sum of I1 and n-1, 1 to m, I1 lambda in minus 1 times something which we denote by d, mi1 minus 1. And these are called mixed discriminants. So this is just a polarization of the determinant as an n-1 of a homogeneous polynomial of degree n-1, right? So it's a function of n-1 matrices of dimension n-1. And it's linear in each argument, just a polarization of the determinant. And if you plug that formula into here, we will get for support functions that are C2, we will get a formula for the mixed area measure. So in this case, it's again absolutely continuous, and its density is the mixed discriminant of the Hessians of the n-1 dimensional support functions of the convex. So it's just the polarization, it's the polarization of the density of this object over here called the area measure. If you want, you can think of this as being, let's say, the nth variation of the volume. So it's some very high order variation of the. Now, what this means is that now we can repeat everything, right? So what does it mean in this case when all of them are C2? So X not being in the support of SC1 to Cn-1 means that the mixed discriminant is 0 on some open neighborhood of X. And the way you should think about this is a kind of multilinear form of the homogeneous motion pair equation. And now the fundamental question that we need to ask, even in this C2 case, is what are the solutions to this multilinear version of the motion pair equation? And the embarrassing fact is that even in the case when all of the support functions are C2, this remains open, which is very embarrassing because, you know, we think of the problems in this case as really arising from the fact that that we have non-smooth bodies and we have a lot of problems, right? But even in the C2 case, we have not actually managed to solve fully this. However, we can try to write down what should be the case. And we want to use the same local to global picture as we have over here, right? So here our intuition was, when is the determinant of a matrix zero? It's when there exists, when the kernel has dimension at least one, right? And that gives us a kind of local linear, infinitesimal linearity. And then there was a local to global phenomenon that actually we can foliate into. So when the mixed discriminant is zero, is something that is well understood for positive definite matrices.
Yes, 3 more minutes.
What?
3 more minutes.
I will do my best. So old theorems, dating back in some primitive form to Frobenius, that if we have positive positive semi-definite matrices and 1 to mn minus 1, then the mixed discriminant, these are n minus 1 by n minus 1 dimensional matrices, is 0, if and only if there exists a vector vi in the image of mi, for I is 1 to n minus 1, such that vi are linearly independent. So you see, I get the determinant. If all these matrices are the same, I get the determinants back. So let's see what happens, right? So if all these matrices are the same, then this being 0 means that there exists a vector in the image of the same matrix. There exists n minus 1 vectors in the image of the same matrix that are linearly independent, right? This should be positive. There we go. So there exists n minus 1 vectors in the image of the matrix, which means the matrix is non-singular, right? So that's if and only. Good. We've sanity checked this thing. But if I have different matrices, then I have to find a vector in the images can be different, but I have to find one vector in each of the images such that these vectors are linearly independent. And if you think again about the local to global, like we think about this as the Hessians, right? So these vectors being in the image of the Hessian, this is the orthogonal complement of the kernel, right? So this is the orthogonal complement of the normal cone, right? So this leads us to the following conjecture. The support is the closure of the set of all directions such that the following holds. There exists a vector vi that is orthogonal to the normal cone containing x for the body ci, 1 to n minus 1, such that the v1 to vn minus 1 are linearly independent. And this conjecture is literally a translation of this local to global phenomenon, but in the context of this theorem over here. So it says now we don't just have one body, but we have n minus 1 bodies. Infinitesimally, we know there are going to be directions where we're orthogonal to the kernel. And now we need to show that we can blow this up into a kind of foliation of the sphere such that all of them are doing. So I have to end, right? So I didn't tell you any theorem. What I can tell you, so here the intuition came from the C2 case, but of course we want this for general code. What we managed to prove is half of this conjecture. We managed to prove the inclusion, this inclusion over here. So neither directions of this conjecture are obvious at all. So we managed to prove this inclusion by some kind of geometric measure theory arguments. And we managed to prove the opposite inclusion to solve the problem in dimension 3 and in a few other cases, and using completely different tools. And unfortunately, we seem to be very stuck in dimensions 4 or higher. And it seems to be that in dimensions 4 or higher, complex bodies behave much more rigidly than in dimension 3. For some reason, we don't really understand very well. And so there's really a lack of methods to study these kind of problems. And in that other direction, this opposite direction where we only prove it in dimension 3, we don't even know how to prove it for C2 support function. And that's just a PDE question in a sense. But it's a PDE question that doesn't seem to be within the normal set of tools that I used to study. So if anybody has ideas or is interested in these kind of questions, very happy for you to come talk. Thank you.
Thank you very much for the wonderful talk. Is there any question?
In the case of polytope, are you all right?
In the case of polytopes, this conjecture is true. And it's I don't know if everybody wants to see it, but I can prove it for you very easily. But this conjecture turns out to be true in all the cases that we know. So there are a few cases where so polytopes we know, smooth bodies where all of the normal cones are one-dimensional. That just means the support is everything. That we know. We know now a few other cases in complete generality. Another one is zonoids. Zonoids are a very special kind of convex bodies. They are limits of sums of one-dimensional segments. These are very special. One has different tools. It's known to be true there. In all cases where we have tools, right? So where we have tools to check, we know this conjecture is true. And now we know that one half of the conjecture is always true, despite the fact that the bodies are not smooth. But it's very embarrassing. It's particularly embarrassing, I think, that we cannot even solve this where the support functions are C2. I mean, that's such a classical kind of situation. We don't know how to approach this.
Is there any other question?
Just a curiosity, there's an interesting relationship between these mixed volumes and the coefficients of the tube, the volume formula for the tube.
Well, I mean, you mean the Weil tube formula is not necessarily for convex bodies.
Exactly.
But if you restrict it to convex bodies, that's just a very special case. If I take a convex body and I take plus t times the Euclidean ball, that just means I took a tube of radius t, right? And well, I mean, we can just write it out because the volume is the mixed volume of k plus tb n plus 1 times. So, I mean, I'll probably do it wrong, but it's k equals 0 to n. So we have the mixed volume of k times. Let me write it up.
Yeah.
And the Euclidean ball n minus k times. Then we have t to the n minus k. Then we have n choose k. So that's the formula.
In terms of curvatures of the surface, this inequality is about the mixed volumes. Say something, I don't know, about the Riemann
Exactly.
contractions of the Riemann of the cone that was differential geometric interpretation.
These mixed volumes are very special, where you have only one body and Euclidean balls. And in that case, the mixed, for example, if these k's are smooth, these k's have C2 support functions. This is exactly the integral over the sphere of the homogeneous polynomial, this elementary symmetric polynomial of degree k of the eigenvalues of the Hessian of hk. So that's exactly what you expect from the Weil tube form.
Okay,
right? So that's just one very special case of this. But they go in orthogonal directions because you see the Weil tube formula is really tied to the Euclidean, let's say the Riemannian geometry, right?
Yeah.
But it doesn't require convexity. And here we require convexity, but we don't need to enlarge by Euclidean balls. We can enlarge by any convex body. And in fact, we can take the nth order. This is just a kind of, you only have two bodies here, but we can take derivatives in any directions and understand all of them. Right? So it's kind of in different worlds, but they have a point of connection.
Let me conclude with one more question. Feel free not to answer. Do you believe the conjecture?
I believe the conjecture. And we just can't imagine what else it could be. And another way to say it is that you usually, You see, we think of any convex body as locally looking like a polytope, right? Just depending on the dimensions of the normal cones, right? So the convex bodies don't look locally flat like manifolds, right? Because they can have corners or they can have edges, right? But let's say I have a convex body that has, okay, so the edge can look nasty, right? For example, you can have a lens. I don't know how to draw it. Right, just a lens, right? It's kind of round, it's round on two sides, but it has this kind of sharp edge, right? This is not a polytope, but if I zoom in somewhere over here, it's flat. If I zoom in somewhere over here, I will see a flat edge, so it will be like the edge of a polytope, right? So kind of the intuition that we have is that kind of arbitrary convex bodies, no matter how nasty they are, if I zoom in to one point on the surface, they should look like a polytope. And in some sense, this conjecture over here, you see, it's true for polytopes, but it's just kind of the localization of the statement for polytope. So if you believe in that kind of principle, that principle doesn't seem to lead to any methods of proof. But but if the conjecture is wrong, then it would give a counterexample to this kind of general intuition, and that would also be extremely interesting. But we wouldn't know where to look.
Thank you very much. Let's thank the speaker again. Thank you.